So welcome to the second day of our GRASP research overview. This is our lineup, and I think I see everyone here, I think. Okay. So yes, okay. So for those of you who are presenters, here's the method. You should join the Zoom, okay? Do not join do not join with your audio, just join, the Zoom, keep the audio disconnected. And then when it's your turn, you will share your screen and then you'll come up here and do your presentation, okay? My name is Hsieh. I'm the Deputy Director for the lab, for those of you who don't know who I am. So I will be moderating. Everyone is going to have 8 minutes, okay? And I will give you a 3, 2, 1 countdown. So I'll sit right here in the front, and then I'll raise my hand and let you know how many minutes you have left. So here's the lineup, and I will go first since I'm moderating. So I'll get to do that. Questions? Okay, without further ado, I am going to go ahead and get started. Oh, I guess we're missing one. Okay, it's not a big deal. We will figure it out. Why is this not working? Hold on. There we go. Oh, I missed a red box. So George, so these are the GRASP faculty who are presenting today. I missed a red box because around George. And let me close this real quickly. And so Nicolaus is here for George, so he will get a chance to see what they do. Okay. And it's great to have Jean here this year. I'm looking forward to that. Sorry, I have my group is the Scalable Autonomous Robot Lab. Our lab is located on Pennovation campus in building 200. This is our current group right now, as well as some of our alums. So what we do, we're mostly interested in being able to do large scale monitoring of ocean environments, actually just about a lot of different kinds of fluid environments, okay? We work predominantly in the ocean. And the idea here is that we want to be able to think about how you use large teams of robots to be able to achieve good coverage, right? So the ocean is really large. It's probably not feasible to really cover it with all kinds of sensors. And so really what you want to do is you want to be able to have teams of air, surface, as well as underwater vehicles, and allow them to adjust their sampling locations based on what the process that you're interested in tracking. So this could potentially be an oil spill. It could be some kind of physical sort of upwelling event in a particular part of the ocean, or it could be you're trying to maximize sort of your chances of being able to rescue human survivors in case of a maritime accident, okay? And so the way I think about this is we want to be able to model the dynamics of the ocean, be able to use those models to be able to do good prediction. And then that information can be used for planning, for control. And then the idea here, so this is kind of this, if you can do that, right, then you can, the information allows you to do more energy efficient planning and motion control of your vehicles. It then allows you to put your vehicles where you need more data that can then improve your models. Because you have such a heterogeneous team of vehicles operating, you have to kind of, you have to solve the control, the planning, the coordination problem. And in addition to that, once you collected all this data using all the different kinds of sensors, you have to fuse all this information into a consistent description of what the dynamics is doing. And so through that, you have to then build models, right, of this very complicated environment. And then hopefully some of those models are going to be informed by your understanding of physics. And then at the end of the day, once you have a really good understanding of the fluid dynamics, hopefully you can then use that information to build better robots that are more effective in being able to harness, right, sort of the forces that the environment is providing on the vehicles in order to do more efficient navigation, okay? So we kind of work on all aspects around the cycle. So here's an example of an adaptive sampling problem. So think about, so the video on the top left, that's the example of a dispersion. So think of the dye almost as if it was an oil spill. And now the idea is, where do you send the robots in order to be able to track the dispersion? And so the model, the grayscale video that is shown at the bottom is basically the reconstruction or the estimation of the process of this dispersion process that is being built using the data the robots are collecting. And so we have a big tank, water tank in the lab. We can actually create different types of ocean-like flows in the lab and then be able to run experiments with robots in order to test and validate our algorithms. Okay. So another thing that so part of this, right, is we're collecting data, and our goal is being able to come up with good models that describe the ocean dynamics. So there's a big component of research in our group that is focused on model learning. You can apply some of these things to your robots, right? So what I'm showing you here, this is my graduate student, Kong Yao. And the idea here is you can use what you know about the dynamics of the quadrotor and then be able to supplement, right, that known dynamics model with data in order to build even more robust model of the dynamics of the system, and then wrap, you know, either standard or more sophisticated controllers around it so that your vehicle can be very robust to different kinds of disturbances. So what you're seeing here is Kong Yao is actually standing on the side, and he's adding additional weights to the quadrotor, and the quadrotor is able to sort of recover from the additional mass, even though that is not, that information is not baked into its plant model. So we can do the same thing in terms of systems whose dynamics now, instead of being described by ordinary differential equations, are now described by partial differential equations. So these are the kinds of fluid processes that we're interested in mapping out in the ocean. And so the idea is the same. Can you somehow leverage your understanding of physics to be able to constrain the learning such that you can do a better job in terms of model estimation, but also potentially do it with a lot less training data, okay? So here's another example. So here we're looking at not just learning model representations that gives us good estimates of what the velocity of the fluid is at a given point, but also be able to give us information about the larger global dynamical structures that actually tells us something about the global dynamics of the system. So what you're seeing here are movies of different dynamical systems of varying complexity. I'm just going to point out sort of the middle double gyre that is actually a model that oceanographers often use as a simpler version of ocean dynamics. And then the bottom one, the Bickley jet, this is sort of a vortex shedding type example. You actually see these kind of fluidic structures around the equator of the globe during certain parts of the year, okay? So the nice thing about thinking about things from a fluid perspective is that, you know, this is relevant to robotics, especially if you're interested in doing coordination of swarms, because swarms are simply a collection of particles, very similar to a fluids problem. And so you can then think about trying to understand the dynamics, right, of these very complex multi-systems in a very similar fashion. And the idea here is, instead of thinking about the dynamics of an individual agent in a swarm, I can think about the swarm as a single agent with, you know, noise. So this is kind of thinking about us describing the swarm using stochastic differential equations. And then if I can do that, I can apply some of these recent techniques in transfer operators in order to be able to figure out how I model the dynamics, right, or the time evolution of the density function, that gives me the solution to the stochastic differential equation. Okay. This has also implications from a robot's perspective, because this means that now if I can have these sort of group level models of what the swarm is doing, I can use those group level models to then think about how to do design of single robot coordination strategies that then achieves the desired group behavior that I want. Okay, and then last but not least, this is work with Dr. Marc Miskin and Dr. Cynthia Sung, where we're trying to understand how different types of platforms, right, interact with the flow field differently, how that can be leveraged in order to do more efficient navigation. I'm not quite sure why this should be playing. Yeah, there we go. That should be playing. So there's our origami robot and the self-assembling mod boats so the origami robot is with Dr. Sung, and then the mod boats is with Dr. Yang. And then just to conclude real quickly, let me just make sure. We also have a project with Dr. Juramek from mechanical engineering, and we're trying to understand how these severe weather patterns can impact our drinking water supply. And so we actually run experiments with autonomous boats, trying to monitor, doing water quality monitoring out in the Schuylkill River. So this is just behind the Pennovation campus. Okay, so next person, Jean. I'm gonna stop my sharing, and I believe Sadie, there we go.
Very low tech, yes.
That's the microphone. You have to speak into the microphone.
Yes. Oh, okay. Yes, my web page, because there's something funny I want to show, so that's the reason. Yes. Thank you. Okay, well, nice to meet all of you. Most of you could be my children or perhaps even grandchildren, I think. Yeah, it's possible. So you probably don't know who I am. In that case, I will tell you briefly. So I had a sort of revelation around 1992, 1993, a little bit like Moses seeing the burning bush, in that movie. The only difference, my hair did not get white after seeing the bush, So my revelation was that I discovered that I really love geometry and I wanted to use it. Until 1992, I was actually doing logic, the lambda calculus. What is that? Program verification, even compiler construction. So then I had this revelation. So what did I do? Well, I took some math courses. This was painful. Oh, by the way, don't do this until you are a full professor. This is way too dangerous. Okay. So anyway, what happened is that CJ Taylor showed up and Costas showed up in the department and Jumbo, and they're shrewd. They come to me, they say, there's this thing, and I get very intrigued. The problem is I never emerge. Once I immerse myself, they're all beyond me and I'm still trying to understand stuff. But anyway, I think there's a value to this. So in fact, what I've discovered, so recently I've been interested in aspects of representation theory and harmonic analysis. What the hell does that mean? Yeah, the Fourier transform, glorified basically. And there are all sorts of papers on something that sounds really fantastic. Group equivariant deep learning in CNN. That's not the TV CNN, the channel, it's a convolution neural network. It sounds even more impressive. So what the hell is that? So I get really annoyed when I see these things. I don't understand the words. What the hell does that mean? So I want to understand. So I start reading these papers, and I discover that these papers, sometimes they're like 100 pages. So the Dutch are very good at this. And 18 pages are readable by idiots, I would say, or, normal people. And then you discover that they state results that require, really advanced stuff. So if you're willing to overlook that, okay. And then you have an appendix. So the appendix is between 40 to 60, perhaps 80 pages. And the appendix is useless. Unless you already know the material, you cannot, condense books that are 400 pages in an appendix. Plus, they're not really prose. I mean, they're very, very good, actually. But, so it's a challenge. And I'm a funny guy. When I get ticked off, I'm really pissed off that I can't read those damn papers. So I don't sleep. My wife said, "What are you doing?" "I'm reading the appendix." I said, we have other things to do. What the hell? We have to take the dye. I said, "Oh, okay." So anyway, I've been reading lots of appendices. And so there's something I do, which I've been doing forever. I don't recommend, once again, until you're tenured, in fact, perhaps full professor, I write. So I write books. So I'm going to show you something. Okay, I'm going to show you something. So how do I scroll down? Wait. Sorry? Yes. Okay, so research and book. Wait, how come I can't? See, I'm not very, okay. Most recent books and papers. So you're going to run away from me. And obviously, when you see this, you say, what the hell? Who is this guy? When does he sleep? Actually, I don't sleep. I'm a vampire, so I don't need to sleep. I sleep in my coffin, and that's all I do, right? So, you see, I don't look my age because, so why is it not going? I don't look my age. How come it did not do that? No, not this. This is, okay. I want to go to something else. I want to go to this guy. Boy, you have control? You control me. Oh, okay, yeah. What should I do? Okay, anyway, so in fact, about 5 years ago, Costas already, he's evil. He said, Jean, there's this thing, And I said, oh, really? Yeah, the Fourier transform. He said, oh, yeah. I thought I knew what it was. But wait a minute. You do that, okay, on SO2, that's the circle. Well, Fourier did that 200 years ago. Okay. But then, you do it to SO3. It's a group. So you have to integrate on a group. What does that mean? Well, you have to do something. And so I gave these sort of informal lectures for about a year, and I intended to do far more, but I got bogged down in the measure theory, and Costas was all pissed off at me. He said, the measure, what is this measure business? Well, you need to integrate. Okay, does that mean 3 seconds or 3 minutes? Okay, that's all right. So anyway, recently I've been writing about equivariant, group equivariant deep learning, and actually it's really incredible. It relies on a lot of fairly fancy representation theory. In particular, you want to generalize the Fourier transform on compact groups. So you have a function, you want to compute the Fourier coefficients, but they're not coefficients, they're matrices of coefficients, it turns out, which is quite interesting. And then given a bunch of matrices like that, you want to come back to the function, and it can be done. But then there's something very interesting, which is that in order to deal with all these things, you discover that you need functions that they call feature fields. So what is that? Well, they define, let's say, on R3 and go into a vector space, not scalar values, but the vector space, there is some what's called a representation acting on it because it comes from a group acting on the thing. So I know it's completely incomprehensible, but these feature fields are very interesting. And then you have to understand how they transform. And then guess what? You have to use what's called induced representations. So if you love that stuff, you're in heaven. You never come out of it. You read obscure books. And then I write, yes, I promise I will not overdo it. So please come and see me. Bring some wine, preferably if you do that. Burgundy, okay, no California whites. Anyway, I will stop right here. That's enough, yeah.
Okay, good morning, everybody. My name is Francis Sowande. I am a third-year mechanical engineering PhD student, and I'm here today representing the Rehabilitation Robotics Lab. So our lab is led by Dr. Michelle Johnson, the big person in the middle, and we are a group of people from diverse fields, including mechanical engineers like me, bioengineers, computer scientists, people who've worked in rehabilitation, medicine, and even neuroscience. So you're probably asking, why do you need all these people that do all these different things? And well, our lab's goal is to utilize robotic technologies to help people with non-traumatic brain injuries, such as stroke and cerebral palsy. And we do that with a special emphasis on accessibility. One way we want to be accessible is cost, which is a big thing. Healthcare is expensive, especially rehabilitation that occurs over many, many years. However, one theme you're going to see today is we're not trying to take the job away from therapists and professionals, but we're trying to give them more help. A big problem is that oftentimes there are more patients than there are therapists. So if we can give them sort of more faster, automatic, quantitative tests, it's going to make their jobs easier and make it easier for them to see many, many more patients and help them out. So we work with a variety of people from a variety of places, including here in Penn. We work with, therapists at CHOP, Penn Medicine, many labs at Grass, but also people in other countries such as Mexico and the Princess Mariana Hospital in Botswana. Now I'm going to talk about our projects. The first one we're going to talk about is the rehab care system. And rehab cares started out as a community-based platform for rehabilitation. So it was a system with a bunch of different stations that basically allowed one therapist to see many, many people at the same time. And one of the benefits of this is that there was research showing that if people were working at the same time, it would motivate them to, want to work harder and encourage each other. But there was one standout part of rehab cares, and that was the TheraDrive robot. You can see there in the blue, and TheraDrive is a 1 degree of freedom, like robotic arm sort of system that allows us not only to perform assessments, but also provide rehabilitation. So, if we change the stiffness of the motor, we can learn a lot of things. And we can also change the orientation of the TheraDrive so we can change the primary axis of rotation. And TheraDrive features, a variety of games that, once again, collect data for assessment, but also provide rehabilitation. The primary groups we look at with the TheraDrive system are people with stroke, sort of, because stroke does tend to affect a lot of upper limb rehabilitation. That's what TheraDrive is for. But also we look at the intersection between stroke, HIV, and aging, because, there's been evidence that if you have HIV, it affects your chances of getting a stroke. And we're also looking at how having HIV sort of affects, not necessarily your age, you're not going to age faster, but like sort of how it affects your body and what your body can do. And you can see here pictures of people using the TheraDrive with the various games. And even the one in the middle with the white system is, again, with our partner in Botswana. For this TheraDrive, there are a couple of sub-projects, the first one being the TheraDiad. TheraDiad is basically 2 TheraDrive systems that are haptically connected. And so it allows us to explore what people working together can do. So, if you have somebody that's less impaired with somebody that's more impaired on there, it's like, can they learn more, learn faster, as well as, but what if you have 2 people who are impaired, and just sort of seeing how these haptic connections can be a benefit to standard rehabilitation with the TheraDrive. We also have biosensing. So we're adding metrics that are to our data collection. So to give us more of an idea. So we're using EMGs, IMUs, ultrasound, contact sensing agents to get more robust and sort of larger data when we collect data. Next, I'm going to talk about BiADLER. And BiADLER is a system built for people with bilateral impairments, such as stroke, which means one side of your body is more impaired than the other. And so with BiADLER, we have an active and a passive arm. And the idea is that you put you put the more impaired arm in the active arm and the less impaired arm in the passive one. So as you move the passive, it collects data. And based off of that, we're investigating how we can inform the movement of the impaired arm. Next, we're going to talk about my favorite project, because this is what I work on, but this is the Panda Gym system. And the Panda Gym, unlike all our other projects, focuses on infants. And so there are certain impairments you can be born with, such as cerebral palsy, but they don't have a cure. The one thing we can do for people with CP is provide therapy, motor therapy. And evidence shows that providing this therapy before the age of about 1 or 2 is most effective. However, the testing for such impairments before the age of 2 is limited. It's, again, inaccessible. There's not enough therapists to provide it. So we put together this sort of play gym system that allows us to collect data and to investigate what are some early signs. And so we have 3 main modalities of sensing. The first being, you can see here, the Panda toy. It's an in-house built system. It has FSRs, pressure sensors, IMUs, and just to see how much interaction the infant is doing with the toy. It also has like lights and sounds to make it fun for them. We also have a variety of cameras to collect computer vision data. And one annoying thing is that a lot of human pose recognition with computer vision is done for adults. So we have to train whole new systems for babies. And finally, we have a pressure mat, and the pressure mat collects something called center of pressure, which gives us an insight into sort of movement and balance. And you can see you can see the video isn't playing up there, but in that large sort of white screen, this is an overview of all the data we're collecting and how it's synced up live. Similarly, there's sub-projects under this, the first one being the lossy sensor, which is in collaboration with the Colab. And this is a lattice structure, 3D printed sensor, and with fiber optics woven into it. And by compressing the sensor, we're able to sort of see changes that allow us to quantify the compression. And we're working on applying it to the Panda toys you can see in the bottom there and seeing if getting a softer sensor, something that's more robust. There is the infant simulator project, which is basically a robotic infant used to collect movement data and motion data, so we can see the intersection between sort of the motion we see from computer vision as well as the center of pressure and how these things inform impaired versus non-impaired infant motion. Finally, I'm going to talk about Flow. I got 1 more minute left. Flow is a combination of a telepresence robot as well as a social robot. So Flow has, you know, a very, very expressive face. It has arms that allows to move. And so Flow is there to help collect data, computer vision data, sort of the same thing as some of the other products we have. And it's generally meant to make it a pleasant experience for the person while being able to go far away to where they live and, you know, help with that form of inaccessibility. We have more projects where we explore how using brain imaging and machine learning to quantify impairment and stroke. We look at safe robot-assisted therapy as well as learn non-use and video-based action analysis. And there's many more things. And if you want to hear about more in more detail, here's the contact information for our PI, as well as all the PhD students and our website as well. Thank you so much. Give you time to take pictures. And here's my lovely lab members and I this past summer. We had a good time. Thank you. Have a great day.
Hey, folks. I'm Jake Welde. I'm a 5th-year PhD student in mechanical engineering in Vijay Kumar's lab. And obviously, he isn't here today, so I'm going to present on his behalf a little bit about our lab. So you can see here some of a pretty complete list of some of our students and postdocs and research staff. Our students are fairly evenly spread across the 3 departments that are the primary departments of GRASP. And you know, our students come from a wide range of institutional backgrounds, countries of origin, personal backgrounds. And I think that all that together and our, you know, wide range of disciplinary interests is one of our strengths. I think our lab works on a lot of different areas of research. And something I've really enjoyed as a student is getting to work really close by students working on very different projects that I'm working on, which has sort of expanded my perspective a little bit. We also have several postdocs, like I mentioned, and some research staff who work on maintaining and operating a lot of the experimental equipment that we work with. So one of the areas that we're interested in is enabling aerial robots to have sufficient autonomy to complete practical tasks despite their severe, what we call swap constraints. So swap constraints are size, weight, and power constraints. And when we're interested in flying very lightweight vehicles, we can't carry heavy processors and sensors on board. And so for that reason, we work with vehicles like this 250-gram quadrotor on the left here, which has onboard cameras and an inertial measurement unit, as well as a cell phone grade processor. And using the information coming from these sensors and only the onboard processing, this robot's able to estimate where it is in the environment, as well as detect obstacles and goals in the environment to complete a useful task. To target even we target even smaller vehicles when we're interested in working in extremely confined and cluttered spaces, like the Tercel on the right over here, which is about half the weight of the vehicle on the left, and is designed to be able to be robust to collisions with the environment. In addition to being robust and not crashing when making a collision with the environment, this vehicle can actually use these collisions to inform itself about the geometry of the environment and even build a map based on this information. To enable more complex tasks, we use these robots as part of a multi-agent system or a swarm, as you can see on the bottom left here. And to enable these systems to complete more complex objectives, we often use a representation called a graph convolutional network that allows these robots to learn skills in a way that's compatible with the sort of intrinsic communication and interconnection constraints and conditions that this multi-agent system has. We're also interested in how to physically control these systems to make them move through the world in the way that we want them to. So here you see an aerial robot, a quadrotor, equipped with a 2-joint robotic arm, and we like to manipulate these blocks in the environment. To do this task requires 6 degrees of freedom control over the position and orientation of the gripper, but the arm only has 2 joints. And we're able to accomplish this by sort of jointly recruiting the degrees of freedom of the arm and the agility of the vehicle to complete this task as a whole. To design a planning and control framework capable of doing this, we use geometric tools that we've developed to identify sort of structural hierarchy in the dynamics of these systems and split their dynamics between sort of the internal degrees of freedom, the joints in the arm, and the pose of the gripper, the external degrees of freedom. We're then able to certify the stability of these controllers by considering the sort of cascaded structure that emerges in their dynamics and provide formal guarantees that if we analyze the stability of these 2 subsystems separately, we can then provide guarantees about the stability of the system as a whole. To tackle tasks in more challenging environments, such as forests, we also work with much larger vehicles, like this quadrotor you can see on the left here, which is about 16 times the mass of the quadrotor on the left in the first slide. And this quadrotor is equipped with a much more powerful processor and more advanced sensors, like the LiDAR that you can see on the very top of the vehicle. It turns out that a lot of the visual navigation algorithms we rely on for those very small vehicles sometimes struggle in environments like forests, where visual features are moving around. If you imagine leaves on branches blowing in the breeze, it can be really hard to identify where you are when those features are moving. And for that reason, we focus on semantic algorithms that rely on landmarks like trees to map the environment and localize yourself within it. The maps that we're able to build with these semantic algorithms become part of our overall autonomy planning and control stack. And this allows us to move throughout the environment while collecting data that can be used in the management of this environment, whether it's a natural environment like forest or an agricultural environment as well. And the last topic I want to mention I guess I have a little more time, but the last topic I want to mention in our areas of research, among others I didn't get to talk to you about today, is work on heterogeneous swarms, and in particular resilience to either failures of individual agents or even adversarial attacks on those swarms. Unlike the swarms that I showed you on the very first slide, often robotic systems are comprised of robots with very different capabilities, whether in terms of locomotion or the sensors that they're equipped with. You can see here, some aerial robots, some ground robots. Robots may be equipped with, different kinds of sensors on the ground robots. And we'd like to enable these heterogeneous swarms to collaboratively complete a task like mapping an environment, leveraging information such as, the aerial robot can see in a less myopic way, but the ground robot can take much, closer readings, for example. And so we design algorithms that allow these robots to collaboratively rely on their different capabilities, and also ensure that even if one robot in the system fails, our high-level coordination can reassign the task configuration in a way that the high-level objective can still be achieved. And so a lot of our algorithms focus on, that notion of resilience, that it's not just about preventing failures, but when failures occur, how can we recover from those failures and still achieve our high-level goals? And that's all I had for today. Thanks so much for listening. I'd be happy to answer questions offline if you have any questions.
Hello, I'm Lingjie Liu, assistant professor in the CIS department at UPenn. I recently joined Penn. My research are at the intersection of computer graphics, vision, and machine learning. My main focus is the 3D reconstruction and the photorealistic rendering. We live in a world that is 3D. That is why we need to understand and reconstruct our 3D world. Here is some things with a very complex scenarios that we need to reconstruct, like the geometry materials of the 3D and also like the dynamics in this 3D thing. And beyond this, we need to control the 3D thing we reconstructed and then synthesize the a photorealistic image synthesis, maybe with the user control. So the problem that I'm mainly focused that can be formulated at this, given multi-view images and their camera parameters, we construct this 3D scene, and we render this from arbitrary viewpoint to get the video. Previously, this is a very difficult problem in computer graphics, and recently the main idea here is that we can formulate this render as a differentiable render, so we can back propagate a gradient to this 3D representation. The main problem here is that how to represent this how to represent this 3D thing. So here actually in computer graphics, we have a lot of the modeling strategies, like to model geometry, material, and also for dynamic things, we have physics. This work, we introduced a hybrid representation, so we can accelerate the rendering speed a lot compared to the previous state of art. For surface geometry reconstruction, we can also not use a previous representation, but use a sign distance field to as a representation to learn this thing. This method is called news, so if you compare with the previous method nerf, this method nerfs without it is quite noisy, and also if you compare with the classical image-based reconstruction method like COMAP, our without it is still better. And this year we further improved this method into a better version. This is a joint work with Costas, and currently we can learn this 3D thing within 2 minutes. And if we want to model kind of this dynamic thing, we already have some model in physics simulation, so we can use this physics priors into this scene representation learning. So here we used Navier-Stokes equation to learn the smoke. And also for human, previously we have a parametric human model, this simple model. We can combine this with the implicit representation. So we know we will learn a better animatable human representation. So here, after you learned this human model, you can also animate this human model with arbitrary motion. And this is a work that we further improve the method to achieve a 4K resolution, high quality rendering. And also, we need to consider more things with the free camera trajectories. Of this is widely used in autonomous driving, such kind of thing. So how to learn kind of a compressed 3D representation for this thing with a free camera trajectory. Besides the geometry, you need also to model the materials in this thing. So here we construct not only the geometry, but also BRDF parameters for reflective objects. And another question is that normally we don't have a multi-view images. What if we only have a single view image? Can we still reconstruct a very high quality 3D representation and high quality rendering? And this problem moves from a 3D reconstruction to 3D generation. That is why here we need a more powerful model here. Here we often used a generative model as a prior to into this framework. And if you No, so first we look at like this 2D GAN model, and this model, I think some of you may already familiar with that. They have like a generator. So you sample like a noise Z in the latest space, and then use the generator to generate a 2D image, and then you train a discriminator to tell this image is a real or fake. However, this image generated is a merely 2D image, so you don't have any 3D information. And our work here is that for the to generate image, actually we can use the like the model in computer graphics. So we use this 3D representation and the graphics rendering method to get this representation. And after that, we can have like synthesize more 3D things. And this is another result. So we train on a class of faces, multiple faces, and then we can generate new face. And here we used like a 3D diffusion models to learn the prior for single view reconstruction and 3D generation. And this work we distill like 2D diffusion priors for single view 3D reconstruction. And also we take a look like the pre-trained like 2D GAN model. We found like this model encode some 3D information. So this if you trained like a 2D guy and you have like you control like some point and you can deform like this object into another space. So we used this funding to another project, which we used a pre-trained 3D model for like a single view reconstruction for reconstruct the shape, normal, and other graphics properties from a single view image. At last, I want to thank all my co-authors. Thank you.
Hi everyone, my name is Fengjun. I am a fourth year PhD student in CIS, and I work with Professor Nik Matni. I'm here on his behalf today to tell you guys about what we do in our lab. So, I mean, for this audience, I don't have to reiterate how much of an exciting time we're living in. Really, like over the recent past, we've seen these amazing things, sci-fi-like things in reality, like robots doing a backflip. Who would have thought of that 10 years ago? But if you zoom in a little bit closer, you would realize maybe there's still a lot of work that needs to be done, especially in terms of making sure that we endow these systems with the robustness to unforeseen factors and also the safety guarantees so that they can be reliably deployed in the real world. And that's something that we as a group care a lot about. So roughly we sit at the intersection of control theory and machine learning. So in control theory, we have a lot of tools to ensure safety guarantees on reliability and robustness. We want to pair that with the versatility and adaptability with data-driven methods so that we can get the best of both worlds. So under this big umbrella, we work on a hodgepodge of things. I'd like to, I guess, highlight a couple main directions that we're working on. And the first one is, I guess, what we call like foundations of learning to control. This is about understanding what makes learning to control easy, what makes learning to control difficult, what kind of systems allows easy learning or difficult learning. This is more on the theory side, and on the more practical side, we care, something that we care about is perception-based control, and also with robustness and safety in mind, how do we control our systems directly from perception, but also ensuring that they're safe. And more recently, we're starting to look into the interplay between the controls layer and also the layers above it, like planning and trajectory optimization, whether we can come up with more principled ways of dealing with the interaction between these layers. This is still pretty general, and I don't have time to go into all of them, so I'm going to zoom in on one particular problem that we have been thinking about over the past year. and it is the problem of imitation learning. I'm sure many of you have heard of this problem. So in imitation learning, you want to control a system, and you have an expert that gives you demonstrations in terms of trajectories, let's say. And what you want to do is to learn from these trajectories, a controller that can reproduce the behavior of your expert reliably. And you can formulate this as a supervised learning problem, and people have done this for a very long time. But one known issue is called distribution shift. So when you're imitating your expert policy, you probably will not be perfect. You will have some small errors, and these small errors compound over time and might lead you to dangerous, lead you to states you haven't seen in your training data. And when that happens, all you can do is to say fingers crossed and hope something bad does not happen. So something we care about in this space is one, I guess, how much data do we actually need to ensure that we can get the safety and good performance of the expert policy? And also, are there any properties of the expert policy or the system that we can make that allows us to say this is an easier case of the problem or this is a hard case of the problem? So I guess this is not my work. This is work done by my lab mates, Daniel Fromer, who was an undergrad in our lab. He's now a PhD student at MIT. And Thomas, who is a fourth year and is in collaboration with Stephen Tu at Google Brain. And so what they've showed through theoretical analysis is that if your expert controller is stable, let's imagine you have a quadruped. Stable means that if you kick it, it will not fall down. The more stable it is, the faster it will be in recovering to the position that you want. So if your expert is very stable, then doing behavioral cloning, you're probably okay, as long as you have a small loss. But if your expert is stable, but not that stable, then you probably also want to match the Jacobian of your expert. So the rate of change when you're in terms of your control, when your states change. And theoretically, as long as you do that, you should be good. And they've done some experiments with Mujoko and showed that there's a pretty significant benefit in doing that. And this is another work done by my lab mate Farhad in collaboration with Tianyu from Professor Nadia Figueroa's lab. Sorry, this is way too complicated and not meant for you to read the diagram. Yes. So here, what they're doing is they're trying to learn a trajectory generation, trajectory generation module. But to ensure safety, they borrow tools from nonlinear control theory, namely control barrier functions, to use as a wrapper around the generated trajectory so that they can ensure safety. And they showed that it can reject disturbances, and Var is going to come in and push the thing in a bit. Yep. And it can also do like reactive obstacle avoidance. So, I mean, this is only a very small part, like the imitation learning is only a very small part of what we do. We are more on the computation and theory side. So most of our students are from CIS, ESE, and applied math. But I also highlight some other stuff that we're doing. So Invar and Bruce are working on some fundamental limits of learning to control, which is like no matter how hard, how good your algorithm is, there's certain things that you just cannot do. Anish and Anusha are co-advised with Professor Vijay Kumar, and they're working with UAVs, and Anish is working on perception-based control, and Anusha is looking into the interplay between the controls and the planning layer. Me personally, I work on the, I guess the theory side, but with distributed control and multi-agent systems. And yeah, that's all I have.
Hello, I'm Nicholas Busius. I'm a PhD student from Professor George Pappas' group, and I'll be presenting today the bulk of the work of our group that can be roughly summarized as safe, robust, and scalable learning-based autonomy. Now, as most of you know, autonomous systems are pretty much everywhere. They're very prevalent these days. And we need to somehow pinpoint what autonomous systems are. One could say they're systems that sense, perceive, reason about our world, and then they act in order to be able to perform some type of a task that is useful to us. This is a gigantic topic, obviously, and there are lots of challenges out there. Our group primarily focuses on these three tasks. The first one is distributed intelligence systems. So we're interested in having multiple agents collaborating in the same environment in order to do some work as fast as possible and as reliable as possible. The second part is going to be about safe autonomy. So agents coexist in the same environment, sometimes with humans or with other robots. So they need to be able to do whatever they're going to have to do as safely as possible. And the third part is about robust machine learning. Well, this has been heavy before. So in this case, we're interested in securing that our network does not do some weird stuff when we have some perturbed input. So let's start on with the first part, the distributed and robust multi-robot autonomy. And there's a number of problems out there, like mapping, environmental monitoring, infrastructure inspection, warehouse operations, that can be cast under the same umbrella term of active information acquisition. And that's pretty much the idea is, we need to design informative paths to estimate a phenomenon of interest. So if we look this through the lenses of target tracking and localization, we have a number of robots, okay, we're giving them. We're given some sensors that are strapped on our robots to sense the environment. And we also have to estimate some model, some phenomenon of interest. So we have some prior knowledge about that, some hidden state. And of course, we need an estimator, some way to merge the information that's coming in and propagate it through the network. Now, given all that, as well as an information measure that we need to optimize, like let's say mutual information or entropy, we can construct this problem in a formulated way. Now, most work out there, what it does, it uses sampling-based techniques to solve this problem. However, what we did, we were using graph neural networks as controllers, and we're training them in an imitation learning way, imitating some centralized sampling-based approaches that exhibit near optimal performance. And what we managed to show is that we get unprecedented scalability, in this case, at least one order of magnitude, upwards, as well as some resilience in loss of communications, and of course, near optimal performance. In this case, you see a video of 3 robots flying over New York, trying to localize some phone booths. I'm going to skip that. So the second part is going to be about safe autonomy. As I said, our robots work in the same environment as humans and other robots, so we need them to be safe. Or they work in an environment that's unknown. So they have some sensors and they're sensing around the environment. So we get some estimate about where other objects are, where other agents are, and some classification about their objects. So like the class and some confidence score about that. And we can construct a semantic map about our environment and use that to actually plan in a safe way. Now, let's say now that we actually have some trajectories, some past experience about what the other agents are going to do. So we can actually use that. Oh, there's something missing there. Okay. We can use that to create prediction regions around the trajectories of other agents, and then do some planning on top of that and have some probabilistic guarantees about our safety using conformal prediction. Now, obviously, the elephant in the room is what the hell is safety? And that is kind of difficult to pinpoint what exactly it is. What we can actually do, what we can actually do is, from expert demonstrations, create some control by functions that describe what's safety for our dynamical system, and then use that as a constraint to create a safe system that is forward invariant in the safe set. And of course, we can extend that to multiple robots. We can also have a risk verification about our system. So we have some controllers, but we need to estimate how safe they are. Using risk measures, it's something we can actually do. And then let's move on to the third part because I'm out of time. So robust machine learning. As you've probably seen before, there are a number of ways that our network are fragile. They break down when we have some perturbation, some out of distribution examples. So that is pretty much the domain generalization issue. We have predictors that are trained using data drawn from a family of related training domains and are evaluated on a distinct unseen test domain. Now, this can be reformulated as an infinite dimensional, as you can see here, as an infinite dimensional statistical learning problem, a model-based domain generalization problem that we can solve using primal dual based algorithms. Of course, we're talking about adversarial robustness, making our neural networks robust. But the problem is, how about the trade-off between nominal performance and robustness? So using classical ERM algorithms, these are accurate, but they're kind of brittle. On the other hand, if we go to the worst case scenario and we use adversarial robustness, these are robust, but they are overly conservative. So we can actually go in a way to probabilistic robustness. This kind of overcomes the trade-off between performance and sample complexity in our algorithms. And finally, we may not just be interested in creating robust classifiers, we may be interested in saying, how robust is my classifier that I've already trained? And to do that, we can kind of look into the Lipschitz continuity of our neural network. And that's pretty much what Micah did back in 2019. They formulated this Lipschitz estimation problem as a QP problem. And by iteratively solving it, they found an efficient and accurate way to estimate the Lipschitz constant of neural networks. Thank you very much. This is our group. So I don't think some are missing actually, but yeah, thank you very much.
Hi, everyone. My name is Cynthia Sung. I'm an assistant professor in the mechanical engineering department here. And our group works in general in compliant and origami-inspired robots. So our group is interested in a couple of different subfields of robotics. On the one hand, we're interested in computational robot design. That is, how we can design custom robots and create software or algorithms to support that design process. So part of the work that our group does is creating representations for robots and software for supporting people as they combine different parts together and to tell them how well that robot is going to work, how they can fabricate it, etc. We're especially interested in origami as a method for actually fabricating these robot designs, because we believe that planar fabrication processes allow us to integrate electronics, actuators, sensors directly into a robot body. And they also allow us to assemble these robots quickly and cheaply so that you can very quickly have a custom robot on your desk in front of you. Because these origami structures are made of thin sheets, a lot of times we have to do modeling of compliant mechanisms because we need to understand how these structures are going to bend under load or how they're going to be actuated. And because these origami structures also allow us to deal with shape-changing structures, we are very interested in how we can take advantage of reconfiguration as a method for allowing robots to gain new functionality. So combining all of these topics together, the main question that our lab is interested in as a whole is how do we more formally think about compliant and origami-inspired design in the context of creating new robot functionality? So these are videos of some of the projects that we work on in the lab. I'm going to today go in depth in three specific projects so you can get an idea of particular areas that we're interested in. So one of the questions that we're interested in is how do we take advantage of soft structures to create energy efficient locomotion? So Professor Hsieh already showed you some of these videos. One of the platforms that we're working on right now is an underwater swimmer, where we're very interested in how we can take advantage of the fact that origami is soft in order to create a robot that can propel itself through the water by generating jets. So this video that you see in the bottom is an origami skin that's being pulled by a tendon and then released. When that happens, the skin changes volume. So when the robot is placed in the water, now the robot can ingest water and then expel it very quickly to create a jet that it can use to propel itself through the water. Our version 1 of the robot, we calculated how much energy it takes to move itself forward, and it's approximately the same cost of transport as a biological squid of the same size. And what we're doing now is trying to iterate over the design to see how we can further optimize the design in order to make it better at this sort of swimming locomotion. Similarly, in another application space, we're also interested in how we can take advantage of compliance to do running and hopping tasks. So what you're seeing here is a pneumatic robot that can jump on this ground platform that you see on the bottom. And the idea here is that when robots are trying to interact with different types of environments, then they also need to be able to tune their compliance, because running on concrete is different from, for example, running on mud. And so in both of these projects, we're interested in what are the particular design techniques that we use to create these soft structures, and how do we manipulate the stiffness or the damping or other mechanical properties of these structures in order to make these robots more energy efficient and also adaptable to the environments that they're in. On the other side of the spectrum, we're also interested in thinking about how we can create algorithms for designing these robots. So most recently, we've had a new result, which is that actually any manipulator arm that you want to design, you can create through origami. And we have algorithms that allow you to translate kinematic specifications directly into origami patterns. We've shown that these work on a variety of arms with many different degrees of freedom. And now we're trying to extend that theory to more complicated kinematic structures. So, for example, a hand is very different from a serial manipulator arm because a hand is a tree-like structure, right? And so what we're trying to do now is think about, well, if we know that we can create arbitrary origami chains, how do we extend that theory now to more complicated robotic-like structures like hands? With all of this, we've started to more recently to delve into the questions of then how do we start to think about controlling these structures? So we think that in the future, soft robots and origami robots are going to have actuation distributed through the entire robot body. And there's an interesting question as to how controllers are going to be able to control these structures in a robust and distributed way so that we can reduce computation. So we've been working on algorithms for distributed control of tunable stiffness structures that allow us to manipulate the stiffness distribution over, in this case, a compliant manipulator arm to get it to converge to particular desired configurations. Combining all of these together, I'm very excited to announce that we also have now a new project in thinking about how we can combine ideas in design and ideas in distributed control to help robots deal with unknown environments. So this is a new project that has recently been funded by NASA. It's a joint effort between my group, Professor Marc Miskin, Professor Doug Jerelmak, Professor Dan Kodacek, and Professor Fei Chen at USC, where we're interested in thinking about now how we can combine robots, mobile robots, into interesting truss-like structures to help them both navigate environments safely and also perform rescue maneuvers to help robots that have gotten stuck. Overall, the idea behind this project is that, let's say that you have a team of robots and they're navigating this unknown environment. The proposal is the moon. And as they're doing that, they learn something about the environment that they're in. Let's say that as they're navigating that environment, one of them finds out that some sort of terrain is risky or it gets stuck. Well, in that case, then we can take advantage of hardware that's been developed at the Grasp Lab in Marc Yim's group to connect these robots together and figure out how they can apply forces to each other to help them get out of these dangerous situations. So in this project, We're really interested in thinking again about how we can design these combinations of robots, how we can control these combinations of robots, how they can detect more information about the environment, and use this information in order to provide an entire team of robots with greater functionality. All of these projects are, of course, led by the students in the lab. So these are the heroes of our lab. If you have any questions or any interest in working on these projects, feel free to reach out to me or to them. Thank you.
Hi, everyone. I'm Marc Miskin. I'm an assistant professor in electrical and systems engineering. And I'm going to tell you about what my group does. So we're the Tiny Robots group. Everything we make in some form is some form of robot that is really, really small. So up on the screen, you can see a bunch of the different types of robots that we've built, and you can see their morphologies. The types that we build are all very different. So there's a biped in the top left. There's a hexapod walking around next to that, or there was a minute ago. There it is. There's one on the top right that kind of crab walks. There are kind of these jet thruster things on the bottom. And so there's kind of a diversity of different types of robots that we construct. But all of the robots in our lab have at least 4 properties in common. So I'll briefly tell you about that. Oh, there we go. Okay, so the first thing that all these robots have in common is that they're all so small that you can't see them by eye. The easiest way to prove that to you is to take these robots and put them into some pond water. So that big thing swimming by right there, that's a paramecium. In the middle frame, that's one of our robots hanging out with a water bear. And then all the way on the right, that's one of our robots next to an amoeba. So every single one of our robots is really, really, really small. They're quite literally microscopic. They're under 1 millimeter in characteristic dimension. And in many cases, they're comparable in size to microorganisms, which is kind of cool. The second thing that all of our robots have in common is that they all carry some form of onboard silicon electronics that they use for processing information, supplying power, doing things that robots do. So here's a fun one of these. This is a little robot that was built now by my postdoc, Michael Reynolds. It's got an onboard clock made out of 180 nanometer CMOS, so something you would have found in like mid-90s electronics. That clock is driving an alternating tripod gate on this robot, causing its little legs to shuffle around. And it's powered by a little onboard solar cell. And so this robot runs on about daylight. If you take it outside, it wakes up and does its thing. So a big theme in our lab is that we're really interested in not just having things that move around at small scales, but things that also integrate electronics like macroscopic robots do, so that you can have some information processing and some kinds of power and autonomy. The third thing that all our robots have in common is that we not only like semiconductor parts, we like building things like semiconductor components. So one of the best ways to make things that are tiny is to hijack the technology that we've developed for microelectronics, but now repurpose it for using robots. And so in our group, we're very careful to make sure that every component of our robots can be built the same way that we make microchips, which allows us to inherit a lot of the scaling properties that you see in commercial microelectronics. So for example, we build our robots on little 4-inch discs about the size of your hand. You build about 1 million robots on each disc. You can dice them up into little chips like this one, where it's about 10,000. And fun fact with microprocessing is complexity is more or less free. So you can make every one of these robots different. You can make every single robot exactly the same. It's totally up to you. And of course, they're also insanely cheap. So if you make 1 million robots on a wafer, the cost per robot is about a fraction of a penny, which is another kind of cool feature of these machines that we get by adopting this manufacturing platform. You know, we have tricks too for actually deploying these. So it's not enough to just have a big wafer of robots. You actually have to figure out how to get them off that wafer and into the world. This is actually where a lot of our effort goes, honestly, but it makes really cool movies like this at the end, where you can see you can make these little swarms with 10,000 little robots ready to do your bidding in your tiny drop of water. Number 4, the fourth thing that these robots all have in common is, since they're microscopic and since you've released them, you can kind of treat them like chemicals, which is an interesting property of these devices. So we routinely move these things around, and with pipetting, we move them around by putting them in vials. We store them in little tiny containers in our fridge. It's kind of cool to have 10,000 robots sitting in a cup or in a microscope drop or whatever. But it's a big difference, again, the macroscopic robots. They're more like doing chemistry or biology than anything else. And you can suck them up, inject them back out. They're perfectly fine. So in the brief amount of time that I have left, what I have, like, how much time? Awesome. I'm going to tell you about our smartest robot, because this is kind of the most interesting one for this audience. So this is a robot. It's our smartest one. It's our 3rd generation micro robot. We call it SmartBot because it's smart. We're running out of names. And I'll walk you through some of the things that we packed onto it. So what you're looking at here, this is the circuit floor plan. This is what goes to the semiconductor facility for manufacturing. And this is a tiny robot. It's our biggest, but it's still pretty small. It's about 2 hairs widths by 3 hairs widths. Hairs width's about 100 microns, so it's 200 micron by 300. This one's powered again entirely by solar cells. It was engineered again to run on about daylight, and we've tested that. You take these things outside, they wake up, they do what they're supposed to do. This one has some sensors. So it's got two classes of sensors, thermometers, and then little voltmeters, so it can measure electric fields and water around it. It has a special little communication module, so you can write instructions to this robot and tell it what to do, and it's all optically done. So you do that by flashing varying intensities of light, which the robot can decode into bits. And then it has little contacts and circuitry for driving its actuators. This is going to come in two classes, so one that propels itself with electric fields and one with legs. The one that propels itself with fields is done. And a little processor and a memory stack sitting inside. So here's one of these devices, all that stuff packed into a tiny little space that fits just about in the 0 of the 2020 on one of these coins. I'll skip through this in the interest of time. And so you can do fun things with these little guys. So you can write instructions for these robots and tell them to execute sequences of prescribed motion. So here's a robot going straight, and now it's going to turn. It's doing this all by itself using its little tiny controller for processing timing. And then it's going to do whatever, shuffle sideways. You can do fun tricks with programming. So the robots also have names. You can tell one robot to do one thing and then another to do something else. So here we're telling the left one to turn. We're telling the right one to sit there. And then after a while, we're going to tell the right one to turn too after the left one's done doing whatever my student programmed it to do. So I guess turn and then shuffle sideways or something. So now this one's shuffling and then the one on the right turns. And we're really excited about I could, but then I won't get students. That's the, they'll be scared. True. That's true. So Rusna is right that in general, if you think this is cool, our world is really weird. So everything is backwards for micro robots. There's no inertia, there's viscous drag. It's hard to walk because the floor is sticky, not because the energy is high. And a big thing that our lab does is kind of address those challenges to try to build things that are functional. One of the things we want to get to, and I think this is maybe a good place for this talk to end, is that we'd really like it if all of those kinds of problems can be done by us. And then we can give you a robot that we can guarantee works, and then you can do robotics, right? A big problem with micro robots is you spend a lot of time learning how the micro world works and how to fab, and you don't really get to do any robotics at the end of the day. And what we're really excited about is the fact that you have something programmable that has memory, compute, sensors means that you can offload that complexity onto something we've previously designed, and then we can give our robots to people that don't have to think about it anymore, right? You've black boxed all of that stuff. So a big thing my lab is working towards is being able to make general robots for kind of whatever environment and application you want, and do it in a way that's scalable, where somebody can say, give us design requirements of, okay, this is what I want my robot to do. And then a couple of weeks later, we say, okay, here's your robot in a vial, go play with it. And so you can see we're kind of building this thing out. We can build you robots that walk on land, robots that go underwater, salty or fresh. We have all kinds of different sensors. We're working on mechanisms of communication and powering that are different than light. All of these different parts are kind of growing. And I have like 1 minute. That's awesome. So I'm done.
Okay, so that concludes our second GRASS research overview.